You ever wonder how your music app just gets you? Like it knows the exact song you want to hear next? Or how a search engine can figure out what you really mean, not just what you typed? Well, a huge part of that magic comes down to a groundbreaking technology called Word2vec. It completely changed the game by teaching computers to understand the meaning behind our words. And today, we're going to pull back the curtain and see how it all works. All right, here's our game plan. First, we'll tackle the basic problem. How do you even get a computer to understand a word? Then we'll get into the big Word2vec breakthrough. After that, we'll see how it learns from context, how it solved a massive computational puzzle, and finally, we'll look at the incredible ways it's changing our world. So, let's start at the very beginning. The biggest hurdle is taking something as messy and beautiful as human language and translating it into a format that a machine can actually crunch. I mean, really think about that. How does a machine understand language? When we see the word king, we think of royalty, power, maybe even a chessboard. But to a computer, it's just a string of characters. K-I-N-G. There's no meaning there at all. And that's the hard truth. It doesn't understand language, not like we do. At its core, a computer speaks one language, and one language only, math. So our job is to be the translator, to turn our words into their numbers. And the solution is, frankly, beautiful. It's called a word embedding. The best way to think about it is like creating a giant, multidimensional map of meaning. Every single word gets its own set of coordinates, a vector. And on this map, words that mean similar things, like king and queen, are plotted as close neighbors, while words that have nothing to do with each other, like king and cabbage, are, well, they're on opposite sides of the map. Now, this idea of word maps, or embeddings, had been around for a while, but they were really slow and difficult to create. So let's get into what made Word2vec, which came out of Google in 2013, such an absolute game changer. And you know, a breakthrough like this never happens in a vacuum. You can see it here. Ideas were building on top of each other for years, from foundational concepts way back in 2005 to the big launch in 2013. And then it just took off, with improvements and new models that went way beyond just language. So what was the secret sauce? The big idea was actually pretty radical, almost counterintuitive. See, older models used these really complex neural networks with a hidden layer that did a ton of heavy lifting. The Word2vec team just got rid of it. They ripped it out. Now, this made the model a little less precise on paper, but it made it insanely fast. So fast, in fact, that they could train it on way more data, which more than made up for that tiny loss in precision. Okay, so we've got this faster model, but how does it actually learn? How does it know where to put each word on that map of meaning we were talking about? It all boils down to this one simple, powerful idea. The model figures out what a word means by looking at its neighbors. It reads millions, even billions of sentences, and learns that words like France and Spain tend to show up near words like Paris and Madrid. The context is everything. And Word2vec does this in two main ways. On the left, you've got CBOW. It looks at the surrounding words, the context, and tries to predict the word in the middle. So given the cat blank on the mat, it tries to guess sat. Then on the right, you've got skipgram, which does the exact opposite. It takes one word, like sat, and tries to predict all of its neighbors. Skipgram is often the winner for big data sets, even though it's a bit slower. Let's really picture how this works. The model slides a window across a sentence. Every time it moves, it creates pairs. So if the center word is machine, the model learns to associate it with make, in, the, and likeness. It does this over and over and over, millions of times, each time slightly tweaking those vector coordinates until they get really good at predicting the context for any given word. So, removing that hidden layer was a huge win for speed, right? But it created a brand new problem, a massive new bottleneck. At every single training step, the model had to solve this giant computational puzzle. And here's the puzzle. That final layer, called a Softmax, has a really tough job. It has to look at the model's output and calculate a probability score for every single word in its massive dictionary to figure out which one is the most likely correct answer. And that's where the problem is. We're not talking about a 20-word vocabulary. We're talking about hundreds of thousands of words. So for every single training pair, the computer had to run a huge calculation for all 100,000 plus words. It was a computational nightmare that basically wiped out all the speed they had just gained. But of course, the researchers came up with two incredibly clever solutions. The first, Hierarchical Softmax, was like giving the computer a super efficient filing system instead of a giant messy pile of words. The second, negative sampling, basically said, hey, instead of worrying about all the wrong answers, let's just check the right one against a few random wrong ones. This is where the sheer genius of hierarchical Softmax comes in. Instead of going through a list of 100,000 words one by one, the vocabulary is arranged into a super efficient tree. Now, to find the right word, the model just has to make a few simple left or right decisions to navigate down the path. This changed the problem from a massive linear search to a tiny logarithmic one. It's the difference between looking for a name in a phone book page by page versus using the alphabetical tabs. It made everything possible. And with that final piece of the puzzle solved, the floodgates opened. Word2vec was ready. So let's look at the incredible real-world impact this new ultra-fast way of understanding language really had. At the end of the day, it was the speed that unlocked the magic. For the first time, researchers could train their models on just colossal amounts of data. We're talking over 30 billion words. That's a scale that was just unthinkable before. And just like a person, the more the model reads, the richer and more nuanced its understanding of language becomes. That massive scale is the source of its power. And that power isn't just theoretical. It's in things you probably use every single day. Spotify recommends music by treating songs as words and your playlists as sentences. The same core idea has been extended to analyze entire documents and even to understand what a piece of software code is trying to do. And the model's simple design made it absolutely perfect for parallel computing. You can split the training data into chunks and have a bunch of processors work on it at the same time. It's like having a whole team of people read different chapters of a book at once to finish it faster. This just sped things up even more, making it even easier for everyone to use. So all of this leaves us with a pretty mind-bending question. The fundamental idea here is representing complex things as points on a map. We've done it for words, we've done it for songs, for software code. So what's next? What other parts of our universe can we teach machines to finally understand just by looking at the company they keep?